Oh, hello, everybody. Again, this is Nate Snydecki. This is our Mechanical Engineering Department seminar. I'm pleased to introduce to you guys one of our newest faculty, Aniruddh Vashisth, who's will be an assistant professor starting in January. So he's in the phase now where he's the acting assistant professor, incoming here to UW. Aniruddh has an extensive background in mechanics and composites, manufacturing. So he did his undergraduate degree at IIT Banaras Hindu University. And then he came over to the United States, did his master's degree at both his master's and his PhD degree at Penn State. He was working with Charles Backus and Adri Van Duyn. He then did his postdoc. He's doing his postdoc currently at Texas A&M in the chemical engineering department with professors Micah Green and Mohammed Naragi. Aniruddh has a number of quality publications, quite an extensive starting point for him as a new assistant professor. But he's also had some very interesting awards as well. He's received the Distinguished Teaching Award scholarship while he was at Penn State. So that's a nice accomplishment for himself. And then he's had a number of conference presentation poster awards as well throughout his time. Today, he's going to be talking to you guys about radio frequency fields for manufacturing composites. So I thank everybody for attending. And just so we have a kind of ground rules, Aniruddh will be presenting, and I'll have you guys be muted until we move into the Q&A session, when then we can start to have you guys ask questions. If you do have any questions, feel free to use the chat feature. And it sounds like we also had some confusion with which room to be in. So I think hopefully we'll get that cleared up as well. But without further ado, I'll let Aniruddh go ahead and get started for us right now.
Thank you. Thank you so much, Nate. And thank you, everyone. Thank you, everyone, for attending this talk. I'll be talking about the work that I've been doing at Texas A&M using radio frequency fields to manufacture composites. Initially, my thought was to name this talk what if Superman helped you to cook composites? But then I thought, I'll just go with something more conventional. So I'll start off with this very interesting graph that pretty much I show before any of the presentations that I give. It's a graph by Michael Ashby of famous Ashby plots, and he shows that I don't know. Can you see my mouse? You cannot. Let me try to do one thing. Can you see the pointer now? Okay, perfect. Okay. So this is a very famous plot by Michael Ashby, and he shows the relative importance of different type of materials that we have been using as that has been used by human beings. And interestingly, he says that he shows that in the last 30 years, ceramics, composites, and polymers, their relative importance has shot up dramatically. So I'm really fortunate that my area of expertise, the area where I'm working, falls really nicely with these three types of materials. The centroid of my expertise is mechanics of materials. That's what I do. So as a researcher, I've worked on a bunch of different projects which were geared towards mechanics of materials. So for example, during my PhD, I worked a lot on fiber composites, manufacturing, analysis, testing of fiber composites. This was a project funded by Army Research Lab and NASA. So we were looking at ballistic tolerance of helicopters. We actually made a Black Hawk drive shaft at the end of this project, which was pretty cool. Another area that I'm actively involved in and plan to pursue in future is freeform additive manufacturing of thermosets, ceramics. I've also worked on bio-inspired composites. So this is another area that I plan to work in the future. My lab will be working actively in this area as well. Apart from experiments, I do some simulation work as well, specifically for reactive molecular dynamics. So let's say when you have to simulate really large dynamic systems and you want to see how some chemical reactions are affecting the thermomechanical properties of the material, the best way to do it is by using reactive molecular dynamics. You can see here on the bottom left, there's a polymer that is getting attacked by atomic oxygen. So if you want to look at a bunch of different polymers that you can use in a satellite in lower Earth orbit, the best strategy would be to screen most of them using molecular dynamics rather than taking them on a satellite and testing them in lower Earth orbit. I've also worked on polymer-derived ceramics. So this is another area where my lab would have a thrust in. These are basically polymers that are cooked at really high temperatures, and you end up with ceramics. Of late, I've been trying to develop some strategies for finite element methods for damage. So there's like some overlap here between like bio-inspired, like this is like a spider's web, like try to make like interesting material choices for a spider's web, and like damage in a notch coupon. And finally, rapid manufacturing. So this is the work that I did during my postdoc, and this is what I'll be talking about today. So using radio frequency waves specifically, so in the electromagnetic wave, we specifically look at radio frequency waves, and I'll tell you like why we are actually focused on radio frequency waves rather than microwaves, and I'll just expand on this area of the research. So first, I'll start off with this very interesting video. Please do not try this at home. This super smart person tried to cook carbon nanotubes in a microwave. So you can see that there's like some sparks going left and right. You'll see in a second that actually the beaker starts to become red. And when that's happening, the nanotubes are at a really high temperature, and of course, there's an explosion. So this was kind of the inspiration for the work that I'm going to show you. It was I was kind of fortunate that when my postdoc advisor's lab started to work on this, like I just entered his lab at that time, so we did a bunch of interesting stuff. But the motivation was like a video that was on YouTube. So let's start with a very basic question: what happens when you microwave food? So microwaves usually they run around run at 1.5 kilowatts of power. So what happens is, like, as soon as you switch on your microwave, the water molecules in your food, they start rotating like tops, just like spindle tops, and they basically bang into each other, create a lot of friction, and that heats up your food. Now, what happens when you put a metal in a microwave? Everybody says, do not put metal in microwave, and that's good. Like, do not put metals in microwave. Metals don't have any polar molecules. They don't have any water molecules in their molecular structure. So there's no good way for the wave energy to actually get dissipated as heat. So instead, what happens is that these metals actually act as mirrors. So the radio frequency waves comes, they basically get reflected. And fortunately, whosoever designed the microwave, he made it as a Faraday cage, so it doesn't come out. And basically, all of that is kept inside the microwave. But if you put a pointed material, or a pointed, like a tip type of material that has like a strong, sharp tip, there's a really high electron density that builds up at these points. And basically, that is when you have sparks, or you can actually end up with fire as well. So metals, otherwise, they have loose electrons on the surface. So if you think about the molecular structure of metal, it's basically a sea of electrons, and you have these positive atoms like floating in it. So basically what happens is some of the energy also hits the sea of electron, it shuffles it, causes a surface current as well. So what causes this heating? So there are two types of people you can ask, like, what causes this dielectric heating, or heating by electromagnetic waves? So let's say first you go to an electrical engineer, you ask him what causes this heating. He'll say that everything is dependent on this equation of power density, that basically the power that will be dissipated, it's proportional to the conductivity of your material and the strength of the electric field inside the material. So let's consider two cases. The first case is that you have a very low conducting material, let's say like your food, and you have your EM waves go through it, and the amount of heat that will be dissipated or transferred from the EM waves to your material would be really low because the conductivity is really low. Well, then you would think that if you have a really high conductivity, that'll be really good. But as I mentioned earlier, if you have a really high conducting material, what usually happens is that these EM waves get reflected. So you're not able to basically cover a really large area. These EM waves are not able to penetrate in a pretty, they're not able to penetrate deep into the material. So again, this results in a really low value of P. And basically this concept is actually used for EMI shielding as well for aeroplanes. So these are basically the two extreme cases that you can think about if you talk to an electrical engineer. And if you ask a physicist, which is already like a not a good thought to do, like, you know, physicists live in their old world, they'll tell you that, you know, it all depends how deep the EM fields are able to penetrate in the material. So the nice thing about polymers is that you can actually tailor their conductivity by adding conductive nanofillers or microfillers. So here on this graph, you see conductivity on the vertical axis, and you have conductivity on the vertical axis. On the horizontal axis, you have the concentration of the nanofillers. So you start off as a non-conductive material, and basically as you keep on loading your material, you end up with like a highly conducting material. And in this curve, you'll see there's one point called as the percolation threshold. And what it basically means is that at this point, if you start off from one end of the polymer, you can just keep on walking on these nanofillers and get to the other end. So if there's an electron that wants to get from this point to this point, it'll have a straight path basically to get to the other end. Interestingly, dielectric heating basically is also dependent on the conductivity of the material. So here is the heating rate on the vertical axis. On the horizontal axis, I have the conductivity. So if you have a very low conductor, when you don't have a lot of nanofillers, you won't get any heating. And when you have a lot of nanofiller, the material is really conductive. Again, you would not get a lot of heating. And this optimum range pretty much lies in this region of percolation threshold, which is very interesting. And I'll talk about this more as we as we move forward. So how would you set up an experiment where you can use these EM waves or these radio frequency waves to meaningfully heat a material that has that concentration of nanofiller in that optimum range? So we'll call that that composite that has that optimum conductivity as our RF susceptor. So you basically make up a gadget which looks like this. You have two capacitor electrodes. A couple of undergrads who I worked with, they used to call it the copper highway. So you basically have a copper highway. So if you look at the side view, these are the electrodes, and you have your RF susceptor. You have an IR camera that basically looks at the heat signature. And this is pretty much what the IR camera looks at. Let's say you have you make a composite with just 5-8% of graphite and epoxy, and you use just 5 watts of RF power. So again, I'll remind you that our microwaves, they usually work at 1.5 kilowatts of power. So here, like, we're just looking at 5 watts of input power. And as soon as you heat as soon as you switch on the power, like, these materials heat rapidly. So this is just 5 watts of power, and it's able to get to 60 degrees Celsius like within a couple of seconds. So this is really good. This was kind of a discovery that was made like a couple of, I guess, like a couple of months before, I would say, like, before I joined Dr. Green's lab. And they found this really interesting application that if you add nanomaterials and you heat composites with RF frequencies, you can heat them really rapidly. So how does that copper highway that I was telling you about, how does that look? So it looks something like this. This is the side view. This is kind of an isometric view. And these are the electromagnetic fields. So as you move further away from the electrodes, basically the strength of the field decreases. And if you want to heat something like, if you want to heat a material which is in that optimum conductivity range, you would want it to be as close as you can to these applicators. Interestingly, we tried a couple of experiments with some other undergrads where we were just like trying to scan with these electrodes. And it's really funny. One of the undergrads, she used to call these type of fringing field applicators death wand, and it just stuck with me. That was like, I was like, never call it death wand. Well, I'm calling it death wand now. So let's see what we can do with dielectric heating. You can do two things, or at least we thought of two applications that we can use dielectric heating for, or RF heating for. So the first is volumetric heating, where let's say you have like a volume, let's say Thanksgiving is coming, like you want to heat a turkey. So you want to heat the whole turkey. So you pass radio frequency waves through it, and you are able to heat the whole volume. The other application is targeted heating, where let's say you want to bond two materials and you don't want to heat the two substrates, you just want to heat the adhesive in between. So what you can do is, if these substrates are either metallic or if they are plastic, and you pass radio frequency waves through it, basically these radio frequency waves don't affect these conductors or insulators, it just heats the adhesive that has that optimum range of conductivity. So what I'll do is that I'll show you applications or the work that I've done for volumetric heating and the work I've done for targeted heating going forward. So let's start with volumetric heating. So the motivation of this work, this was kind of like a silly question that I had. I had a chat with Professor Green, and I was like, do you think carbon fibers would heat? Like if I pass radio frequency through carbon fibers, and do you think they will heat? And he was like, one way to find out. So we tried, we were like, So then we were thinking like, what would be the application of heating carbon fibers? And we were like, there's a lot of pre-preg that is required for making a bunch of different composites. Like the aeroplane is like 50% of it is made up of carbon fiber composites. And before COVID hit, like before COVID threw a monkey wrench and everything, this was a very interesting report that I found that basically that the market for carbon fiber pre-preg is growing dramatically. But manufacturing of carbon fiber pre-preg is a very energy expensive method. So what happens is like you have your carbon fibers, it goes through a matrix and it is heated in large ovens. And these are like big ovens. So, and to heat like such big ovens, you need a lot of energy. Our thought was that, can we use these RF fringing field applicators to like make the process less energy expensive, out of oven, a continuous manufacturing process. So this is like what we wanted to investigate. So we started off, we made a carbon fiber, we impregnated a carbon fiber toe with the standard epoxy, and we basically passed radio frequency waves through it. And yeah, interestingly, they did heat up. So we were really excited about this. So we looked at different types of pre-pregs. We looked at unidirectional, we looked at a 090 weave and a CNT epoxy pre-preg. So I'll show you some of the heating curves and like what we were able to achieve for the unidirectional pre-pregs, and pretty much the other ones had a similar behavior. So the first thing that we do is we call it a frequency sweep. So we look at frequencies starting from 1 megahertz to 120 megahertz, and we basically provide a pulse of 5 watt of power to the material, and we see what is the heating response, what is the dT by dt for the material. And this is kind of a standard graph that we see, and we figure out which is the frequency that's kind of best for this material. And we figured out that it was 66 megahertz. So we tried to cook different specimens at different power, at varying power at 66 megahertz. And if you see, like, if you look interestingly, at just 25 watts of input power, we were able to get to 250 degrees Celsius within 120 seconds. And this is really great. I mean, the nice thing is that we can actually tailor it. Like, as you can see, the input power depends, the input power kind of governs how much you can heat the material. So this is actually like, it's a nice knob that you can actually have a good amount of tailorability for manufacturing your composites. So next, what we did was that we made pre-pregs. We kept them at 4 different temperatures just to see, we kept them at 4 different temperatures just to see what is the degree of cure that we can achieve for these 4 temperatures. And for the highest temperature, for keeping the pre-pregs at 200 degrees Celsius for half an hour, we were able to achieve up to 82% of degree of cure, which is really promising. And just to remind you, I think I forgot to mention this. This was a bifunctional epoxide that was cured with DETDA resin. So these are usually cooked at the initial. It's usually cooked at 121 degrees Celsius to 177 degrees Celsius. So that's kind of the range that you cook these epoxies in. And finally, what we actually wanted to see was that can we come up with a setup where we can continuously fabricate pre-pregs. So this was kind of the last study where like we kind of left off on this particular project, and we were able to successfully show that if you change the translating speed of your pre-preg, if you're translating your pre-pregs over these fringing fields, you can actually increase the temperature of your composites just by changing the residence time for your composites over the fringing field, or having multiple fringing field applicators. You can actually heat up your composites and potentially get varying degrees of cure. And this is kind of where I left off, basically left off the project. And my plan moving forward, once I have an active group at University of Washington, is kind of investigate this a little bit further. Try to see like what are the strategies that we can use to move towards out-of-oven rapid manufacturing. Basically, what are the differences in thermomechanical properties of composites that are cured using this innovative technique as compared to the traditional methods. So next, I'll talk about targeted heating. So most of this work on targeted heating was funded by DuPont. So DuPont, they were really interested in lightweighting of metal structures or like composite structures. And for them, one of the strategies to do that is by reducing the amount of metal that they have in automobiles. So here is a very interesting graph which shows it's basically the inverse of your mileage. So it's liters per 100 kilometers. And you can see a universal trend, everywhere in Asia, in the European Union, in US, that everyone is trying to basically move toward this corner. So basically what you want is that you want to lightweight your structure as much as possible. The way you can do that is by using adhesives instead of fasteners. But if you use adhesives, there's additional challenges that you have. You might have like weird coefficient of thermal mismatches, residual stresses. So that was the problem that we had in hand. So the current state-of-the-art method that a lot of companies, specifically automobile companies, might use is they use IR lamps. So let's say they have these 2 substrates. These could be metals or plastics. They basically come down from top and bottom, and they heat the outer surface, and that heats up the adhesive basically to cure. So if you want to heat the adhesive, let's say the adhesive cures at 80 degrees Celsius, you need to have the IR lamp actually hit much higher temperatures. And again, in the manufacturing industry, time is money. So you want to do everything as quickly as possible. So basically, like it's dependent by the heat transfer problem. So that was kind of our motivation. We thought like, if we can just heat the adhesive, can we have a higher efficiency? Can we use less energy to make this process much more faster and basically move towards rapid manufacturing? So I'll show you 2 examples. I'll show you an example of plastic-plastic bonding in automobiles, and then I'll show you an example of metal-metal bonding in automobiles. So the first example, there's, for example, like the back part of our car has this frame. This is made up of multiple types of multiple plastic substrates, mostly polypropylene. And they usually have a really long bond line where they're kind of like bonded together. A bunch of these are sandwiched together. So what is done right now is that, the IR lamps that I showed you in the previous slide, they basically come from back and forward, and they heat like in a couple of spots. You basically have spot cures so much that the structure can hold together. They look for a green strength. They need like 1 megapascal of strength on these typical sections. And once they have this 1 megapascal of strength, they're like, oh, this is good. They assemble the rest of the car, they paint it and do everything, put it in an oven. And when they put it in the oven, that's when the complete cure of the bond line takes place. So basically our motivation was that we want to use the RF applicators to rapidly heat in these particular spots. So this is the experiment that we carried out. We used 2 types of plastic substrates. Both were made up of polypropylene, but one of the substrates was reinforced by glass fiber. So this is the side section. These are the capacitor electrodes, and we use fringing field applicators. And this is basically what we see in the thermal camera, that we were able to heat just the adhesive and not heat the plastic coupons at top and bottom. Of course, since the adhesive heats up, there's like heat transfer, and your plastic coupons also end up getting heated as well. So let's compare the 2 technologies, the IR bonder heating and the RF heating. So this is the data using the IR bonder that is kind of the state of art right now. So you'll see that LGFPP and TPO, which are these 2 top and bottom coupons, they are able to reach the target temperature of 85 degrees Celsius that is required to cure the adhesive. But within 3 minutes of that window that we were given, that we need to do everything within this three-minute window, the adhesive is still catching up. It actually it does not get to the required 80 degrees Celsius. 80 degrees Celsius to target temperature. Whereas when we use RF heating, we are actually able to get to that temperature within 45 seconds. So this is really good. So we were able to rapidly cure and bond the 2 plastics together using just 1/5 of the energy that was used for the IR bonder. In terms of efficiency, also RF heating was 6 times more efficient than the RF bonder. Just to validate, that we had a good bond using RF heating, we did Lap-Shear experiments. So here is the Lap-Shear, basically the shear stress versus strain curve for IR bonded, and here's the stress strain curve for the IR heating. The 30-minute post is basically the time between manufacturing the composite and finally testing the composite. The target green strength was 1 megapascal. And of course, both of these methods did much better than the target strength that we were looking at. So we can confidently say that we were able to heat the adhesive and basically bond the 2 plastics together using RF heating. We also carried out multiphysics modeling using COMSOL. So this was actually done by one of the co-authors, and we were able, if we know the material properties for the substrate and the adhesive, we're actually able to capture the thermal profile also very nicely. So simulations are really nice. They give you a really nice picture of what is happening, how the heating is happening, and you can see that the heating is happening in the adhesive, and the heat transfer basically is heating up the substrates as well. So next, let's look at metal bonding in automobiles. So again, a good part of our cars are actually made up of metals, different types of metals. There's aluminum, there's steel, and there are different bond lines or sections where 2 components are maybe riveted, or there are like fasteners that are used to hold them together. And the thought was that, can we reduce the number of fasteners here and basically have adhesive bonding in these areas? And we wanted to use RF energy or RF heating to cure the adhesive. So what is the problem of multi-material bonding? So if you want to bond multiple types of metals, it's really challenging. So I'll tell you this, like I'll tell you what the challenge is, the problem of CT mismatch with this really good example of Bender from Futurama, who we all know. And we all know that Bender is made up of iron and osmium. So these are two different types of metals. So let's say you want to bond two metals together. You put it in you put this in an oven, and these two metals start to expand. They'll have different coefficient of thermal expansions, so they'll expand to a different degree. And during this expansion, the adhesive will cure. So it'll try to lock the metals in that geometry. So when you cool down, you'll have a really distorted structure. And if that happens to Bender, he's not going to be happy. So that is basically what we want to ignore. So this is what our setup was for bonding to metals. The nice thing about the bonding metals is that basically your metal acts as the electrode. You don't need that death bond or fringing field applicators. You can actually create the fields between two metals. So for this application, we use Betamate adhesive, which is a commercially available adhesive from DuPont, which was formerly, which was Dow earlier. They had like a weird split up. So the first thing that we did was that we looked at the conductivity for this Betamate adhesive with different concentration of carbon black. So you can see here that as we increase the concentration of the carbon black nanofillers, at one point our conductivity shoots up, and basically this is where we have our percolation. If you look at the heating rates also, you see a similar curve that I showed you earlier. You earlier have, you start off with very low heating rates, but there is this one optimum range where you get the best heating. So we selected 10 weight% of carbon black in our adhesive, and we did like the set of experiments that we did had this concentration. So we did a bunch of different mechanical testing. We did Lap-Shear, peel resistance, and I'll show you this very interesting experiment, multi-material bonding also that we did for this particular study. Before I dive into that, we tried out 4 different methods of curing. So this was kind of our objective to make sure that, when we have different methods of curing, how beneficial is RF with respect to the conventional methods, compared to like a combination of RF cure and oven cure. So the first case was where we just used Betamate, which did not have any nanofiller. We oven cured it. And then we tried out 3 different cases of 10 weight% of carbon black. So the first case was 5 minutes of RF cure, followed by 25 minutes of oven cure. Then the other 2 cases were 30 minutes of RF cure and 30 minutes of oven cure. So the first test that we did was Lap-Shear experiments, where we tried to bond two steel goupons. And you can see the thermal profile here. We were able to get to our target temperature of 160 degrees Celsius within 4 minutes. And we didn't see any significant difference in the shear strength of all the different methods that we tested. There was, I guess, like the base case was a little bit lower in strength, but overall it was fairly comparable. The strengths were fairly comparable. We also looked at the FEM images of all these coupons that we tested, just to make sure that we have a cohesive failure, that we did not have the failure at the adhesive and the metal. And we also wanted to see in the SEMs if there were some weird expansions, or the nanofillers were burning the adhesive. So we didn't see any of those. Like the morphology looked pretty much similar to what we would see for just Betamate adhesive. Next, we looked at the peel resistance of the adhesive. So here we had this coupon, which is like peeled apart, like 2 coupons that are cured and peeled apart. And the average force that you get from a force displacement graph is averaged over a certain length and divided by the width. And here we saw that adding nanofillers did improve this average force per unit width. But again, we didn't see any significant difference for different methods of curing that we were using. So now we get to the interesting experiment. This was the multi-material bonding, or the MMB experiment, I'll call it from now on. So here we wanted to bond an aluminum plate to a steel channel. And the way we did it was, like you can see the setup here. We made the aluminum plate as one of the electrodes. The steel channel was the other electrode. We had fasteners at both ends. And we tried those 4 different methods of curing. And you can see that the samples that were cured in oven had really big deflection, a mid-span deflection. Whereas the samples that had a little bit of RF cure or were completely RF cured had like minimized mid-span distortion. And this is really good. This is exactly what we were actually looking for. If RF heating can actually reduce the CT mismatch that we see in conventional curing of multi-material assemblies. So next, what we did was that we took these MMB specimens, and this is a very interesting type of experiment that is done by the automobile industry. They have a ball joint at one end, and they basically peel off the aluminum plate. So you start off with a 90-degree peel, and you kind of approach a 180-degree peel. So this is how the load versus extension representative curves look like. So for the oven cure, you see that you get a sharp peak, and then you basically drop off to really low load values because you have a really large deflection, mid-span deflection. But for the specimens where you don't have these mid-span deflections, you basically don't get that significant drop. And if you basically look at the area under the curve for these graphs, you can clearly see why RF heating is really beneficial. It reduces the mid-span deflection and increases the energy that is required for peeling off the aluminum substrate from the metal channel. So this is really interesting, really promising. You can see that we see this this benefit both for RF plus oven cure and for a complete RF cure as well. The final question that we had in mind was that, let's say you do 5 minutes of RF pre-cure. Here I showed you that we had this combination method where we did RF cure and oven cure. But how much of that initial RF cure is required to decrease the mid-span deflection? So we did a series of these experiments where we RF pre-cured these MMB specimens to varying time. So we did an RF pre-cure of 4 minutes, 5 minutes, 10 minutes, 15 minutes. And after this pre-cure, we measured the degree of cure that the adhesive achieves. And once we are done with that, we basically put the assembly in an oven for 30 minutes, and we completely cure the adhesive and calculate the mid-span deflection after this final cure. So very interestingly, we see that the mid-span deflection drops down with degree of cure. So this was kind of intuitive. We knew that if you can actually lock these two materials together with RF pre-cure, they will not try to distort a lot when you do the final oven cure. So these were really interesting results. So in summary, we looked at application of RF heating for making carbon fiber pre-pregs, for bonding plastics, for bonding metals. I'm really fortunate that like DuPont is working, they're planning to transition this technology to some of their manufacturing lines. We have a couple of patents also with DuPont on the same work. I would like to acknowledge Professor Micah Green from Chemi, where I did most of this work, all of this work, lab mates who helped me throughout my stay at Texas A&M, folks at DuPont, my family, my friends, of course, my wife's cat, who gives me condescending views that I'm not doing good in my life. She always motivates me to do better. References, these are a couple of publications. These like some of the papers that I published on RF heating. And we have 2 patents which are pending. And with that, thank you so much. And I would love to answer any questions or queries.
Thank you very much. I think we can give you a quiet applause, or I guess we can use the reaction symbols if you guys can. I'll allow you guys to unmute yourselves. So now we're in the Q&A. So thank you, Aniruddh, for talking through all this. I saw there were some questions in the chat. Krishna, are you able to unmute yourself and ask your questions?
Yeah. Hi, Aniruddh. This is Krishna Nadella, and I had a couple of questions on the adhesives themselves, do you think these work on all types of adhesives, or the adhesives have to have carbon material loading of carbon black or some other types of carbon forms?
That's a really good question. So at least right now, all the adhesives that we have looked at, we have had some sort of a nanofiller to increase the conductivity of the material. One thing that you can do, one thing that I basically tried out was I just looked at bifunctional epoxide, and I just mixed it with common curative, and they also heat because they're like polar molecules in the epoxide chain. So you can get some heating that way also. But the trick there is, and this is actually like one of the areas that like, you know, I really want to like pursue in future. Like this is actually a really good question that I plan to pursue and look in future as well. That as you cure the material, their conductivity also changes because there is less and less polar molecules to excite and heat up the material. So as of now, all the materials that we have tried to look at, they have all had nanomaterials in it. But this is actually a fantastic question. This is something that that would be interesting to look at.
Yeah, it seems like water-based adhesive could work, and I can see applications in curing of printing inks in a lot of plastics printing. Typically, they're UV cured or heat cured, but RF curing could be an interesting application there.
Yeah, exactly.
And then the last question I had, Aniruddh, was if there was a skin core composite of some sort, right, where the skin has a higher thermal conductivity and core has a lower thermal conductivity, is it possible to use RF heating to just heat the surfaces at the bond interface and even eliminate the need for adhesives, because the difference in thermal conductivity will concentrate all the heat just on the skin layer and not let it just the heat escape into the bulk of the skin core composite. So that was a question I had.
I see. So basically, you want to bond a skin core, and I think here the electrical conductivity would be much more important as compared to thermal conductivity. I was not sure like if you meant thermal or electrical conductivity. I'm sorry, like I should have made it clear. Like I think like I was looking at the electrical conductivity that influences the RF heating. But yeah, this is actually an interesting application that can be used. And again, you know, it's not just this. Like you can actually make like small antennas. So think of like, you know, the big antennas that we see outside, like, you know, those this type antennas. We can actually make like really small antennas also that can focus all the power. What I was talking about earlier, like that death wand. And you can actually cure or bond elastics like that also. So this is another very interesting area that, you know, that's kind of in my to-do list to mainly look at thermoplastics. If you can bond thermoplastics using this antenna type of approach.
Yeah, I work with Professor Vipin Kumar very closely, and we have an interesting challenge that I think your ideas here can really help. So we'll be in touch. Thanks for your presentation.
Sure. Thank you so much.
So Shen Ren had a question. Shen, can you unmute yourself if you want to ask your question?
Yeah, thank you. Thank you for your great presentation. It's very, very interesting topic. It's actually relevant to my research at the UW as well. And so let me see if I can clear my my question. So because your carbon fiber composite can just apply a very few small power but achieve the high temperature very fast. And the dielectric properties are the temperature dependent properties. So I'm wondering, like, is your composite also have the large dielectric loss at a lower temperature, say the sub-zero temperature range?
I see. I didn't quite catch the last part of your question.
Yeah, so actually we, like at our lab, we're trying to use the RF power to warm up the biomaterials. And for the biomaterials, they also have the small thermal conductivity, but meanwhile, they have a very large heat capacity. And that's why we want to use the like electromagnetic power to do a volumetric heating. And
I see.
But like at our interesting temperature range is maybe like below zero, say -80 to 0 degrees C. And at such temperature range, this composite can also achieve this high absorptivity to the EM power.
Oh, I see. That's interesting. So basically, the base property of the material changes at such low temperatures. That would be interesting. Like I'm not completely sure what would happen, but it would depend on what the dielectric properties of the material are at such low temperatures. If you will be able to get like heating or like whatever you're trying to do. I believe like if you're trying to heat the materials at such low temperatures, I think it'll be interesting to see what the properties are. We actually did try to model the heating in this project as well for the carbon fiber, and it was really tricky because carbon fibers they're anisotropic, like their properties are anisotropic. So it also depends. Let's say this is your unidirectional carbon fiber and this is your fringing field. Like how do you put your carbon fibers over it? Do you put it like perpendicular to the field? Do you put them parallel to the field? So these actually just like small things also have a really big impact on heating an isotropic material, and that's where like the beauty of simulation actually comes in, where you have to look at what are the material properties. We looked at two different types of carbon fibers also. So we looked at T700 carbon fiber, which is like a high strength fiber, and IM7, which is more aerospace, which is more for aerospace application. And IM7 is actually more conductive than T700, and we saw that since the fiber was so conductive that the heating response that we got for that fiber was like a little bit lower as compared to T700 carbon fiber. So like it finally comes down, to knowing the material properties like of the material that you're trying to test. And again, with temperature, interesting things happen. Like for example, for the simulation, we actually for the simulations, we actually had the heat capacity, the conductivity of the material as a function of temperature. So that actually played a really important role in basically tracing the experimental temperature time curves as well.
Thank you. And then I guess my follow-up question is, like, is the carbon fiber composite considered as a biocompatible materials?
As what compatible?
Biocompatible. Let's say we can put them into the biological system, see the cells, tissues, organs.
I see. I know that they were like knee sockets and stuff like that is made with some carbon fiber composites. It usually depends like what polymer you're using with carbon fiber composites. So I know that carbon fiber PEEK. So PEEK I believe is biocompatible, and maybe Nate will know more than I do, but but I know that PEEK is biocompatible. So if you have PEEK, which is carbon fiber impregnated in a PEEK, then I think you should be able to use it with biological system.
I see. Thank you. Thank you so much.
And you want to ask your question, and then we'll get to Matt next.
Sure. On slide 26, you showed the difference in performance between the oven cured and the RF cured. Oh, no, sorry. It was the slide before, I think.
I see.
No, sorry. That one, 25. Yeah.
Oh, I see. Yep.
Yeah, that one. So can you just discuss a little bit what might be the difference? Obviously, both met the requirement, but what are your guesses as to the difference in the performance?
So I think the main reason where the IR bonder might have performed a little bit better than the RF bonded composite is like the time, the duration of heat, like the IR bonder stayed there for a little bit longer. And the way the IR bonder works is that it'll have basically, like, let's say these are the two substrates that you're trying to bond. It'll come from top and bottom and try to touch the composite. So there'll be a little bit pressure, out of plane pressure as well. We specifically did not do that for our experiments. Like we actually just like put them together, like, we tried to have them as close to each other, and we just RF cured that. This is something that, like if you would have applied a little bit pressure also, my thought is that the performance might have gone a little bit higher. The other thing is that the IR bonding test was done by professionals at DuPont, and the RF heating was done by us in the lab. So maybe they have like more polished hands. So there's a bunch of factors that could be there.
Yeah. Do you think the degree of cure might be a bit different in the two cases?
It is possible. It is possible that the degree of cure might be different, because if you look at the data here, the IR bonder actually, my thought would be that the degree of cure would be higher in the RF cure heating. But I guess like the shear strength data is like counterintuitive to that. But like if you see like, the degree of the temperature that the adhesive and IR bonder hits, it's much lower as compared to, we're able to keep the adhesive here at 85 degrees Celsius, which is the curing temperature for almost like more than actually 60 seconds.
Right.
So
right.
Definitely the degree of cure would be, yeah.
Yeah, the curing process, though, I mean, it's going to be a function of temperature also and time, right? Because it's a kinetic process. So, and then I also wanted to ask about the COMSOL results, and it's a problem that hasn't, it's fairly straightforward physics, so it shows good qualitative comparison, but there is some difference, right? And for some curing processes, you really do want to know the temperature quite accurately. So just wanted to hear about your thoughts regarding the discrepancy between your predictions and your experimental measurement.
Yeah, so this is actually, this is actually a very difficult process. I think my appreciation for simulation, like it just went up, like, when I was working with the electrical engineer who was doing these simulations. I guess like there are a bunch of factors that actually go in the simulation. The first factor itself is what frequency that you're using as the input frequency for these particular type of applicators. So the way we were making the applicators was that we would just use our hands to like lay out two copper strips and put a Teflon tape on top of it. But when you're making a geometry in COMSOL, you make it like a perfect capacitor strip, which does not have any undulation on it. It's perfectly flat. So like, I was not sure about this. I didn't know this, but like there are like small geometrical discrepancies that can make big differences. And apart from that, getting the heat capacity, the conductivity, all these different properties which are a function of temperature is again like very challenging for different concentrations of nanofillers. So I personally believe that the multiphysics model it's good, but it's kind of in the preliminary stages right now. I think there's a lot of data gathering that is required for doing like really nice multiphysics COMSOL modeling.
Yeah, I suspect things like sensitivity to dimensional tolerances, those are all things that you could test, right? To see how much your simulation changes when you allow for that variability in the actual prototype versus what you're simulating. But I'm also just noting that as time goes on, the discrepancy between your experiment and your simulation, that grows at the tail end about 40 seconds. Yeah. So I'm just wondering what your thoughts are about changing properties, if you assumed constant properties throughout the COMSOL simulation.
So specifically for this simulation, we did assume that I believe the conductivity and the heat capacity was constant throughout the simulation. So and as you heat the material, like those properties try to move apart. So that could be one of the major reasons that as you move ahead in your simulations, like that you see much bigger differences. Another thing is that we usually do a frequency sweep. I think I mentioned this earlier, where we look at heating rates at different frequencies. So basically looking at how much the heating rate is for different like different set of frequencies. And when we did the COMSOL simulations also, the best frequency shifted a little bit. It was like not 66 megahertz. I think it was maybe a little bit less or more than that. And that was exactly for the point that you mentioned, because of the dimensional tolerances and how much, what was the length of the capacitor electrodes, or if there was like some undulation in the capacitor electrode as well.
Thank you.
I think our last question, hopefully if Matt Bozanetti is still available, he can ask his question. Maybe not. Well, his question was.
Hello, can you guys hear me?
Oh, there we go. All right, there we go.
Yeah. Sorry. How's it going? Aniruddh, thank you so much for this presentation. My name is Matt Bozanetti. I actually work for Boeing as a structural analyst, and I got pointed to this presentation by Professor Kumar. I'm working as an industry mentor for a capstone project this year, specializing in welding of thermoplastic composites. And so I guess that's kind of the thrust of my question is, so I missed the beginning portions of the presentation, but yeah, I'm wondering if this technique can be used to weld peak or PEC thermoplastic composites, right? And I guess the main, like how high of a temperature can we achieve with this process?
Yeah, so thanks, Matt, for that question. And yes, the answer is yes, you can bond thermoplastics using this technology. I think some of my lab mates, when I was working with them, they did try bonding ABS PLA 3D printed structures using this method. The interesting thing is, how do you want to bond these thermoplastics? Do you want to use adhesive, or you don't want to use the adhesive? And I believe the answer would be that you don't want to use an adhesive. So what you can actually do is you can have a thin layer of thermoplastic carbon nanotubes. And one thing that, like, it was a silly thing that I did, that this is going to be the first project that I give to my PhD student. I actually 3D printed a coupon. I believe it was using PLA. I picked up a pencil. I just like rubbed on it with a pencil. I took another coupon and I heated it with RF, and it cured. It just bonded each other. And I thought like that was really cool. So my thought is that, you know, you can actually bond these thermoplastics. It depends like what type of RF susceptor that you want to use. Carbon nanotubes or carbon black might not be like the most eco-friendly way to do that, or something that EPA might not be happy about. But using ink, as Krishna pointed out, like you can use inks, or using, I think like using pencil or a graphitic rub would be awesome. Like you can just write your name and basically bond two plastics with it. I don't know if that made sense or not.
Yeah. So, but I'm wondering how. So for our peak and PEC material system, we typically have to get up to like 700 degrees Fahrenheit for it to really crystallize to form semi-crystalline structure. So yeah, a little more robust of composites. Do you still think that's the case? Is that temperature range achievable?
Yeah. I think it should be. I think it is achievable, and it depends on the type of susceptor you're using. If you're using CNTs, so you said 750 degrees Celsius K?
Like 720 Fahrenheit.
720 Fahrenheit. I think we should be able to get to those high temperatures. It totally depends like how much input power you're using. So for example, you know, if you look at this graph, if you keep on increasing the power, the input power, you can actually get to those temperatures as well. You can get to really high temperatures. I know there was one student who was curing ceramics at almost like 900 degrees Celsius using this method. So I'm fairly confident that 900 degrees Celsius. So I think, yeah, that's really high temperature. So you should be able to get to those temperatures. I think the interesting thing would be like, you know, what type of heating ramp rates you would want to achieve, or using RF energy, does that change basically the microstructure of, or like it changes the polymer, or it might degrade the polymer where you're trying to bond. But I'm fairly confident that if you use carbon nanotubes, carbon nanofibers, or even carbon black, you can actually achieve those temperatures. I would say in less than 500 watts of input RF power.
Okay. Yeah. Cool. That makes sense. Yeah. So I think the
Yeah.
plan right now is to attempt to do a type of ultrasonic welding.
I see.
But we're also kind of investigating, right? Putting our investigation hats on and see what other options are out there. So this is really cool. I might, once the project gets going, point the students back to you, and we might have to have some more follow-up conversations. This is really cool stuff.
Yeah, that'll be awesome. Thanks.
Well, thank you everybody for coming, and thank you, Aniruddh, for giving such a wonderful talk. I think we should give another round of applause for you as well, and we'll look forward to seeing you on campus, or at least remotely on campus, coming in January.
Thank you. Thank you so much. I'm really excited about moving to Seattle, and hope everybody has like wonderful holidays.
You too.
Bye, everybody.
Thank you.